Let's start understanding RAG from the very basic. We'll be discussing RAG with respect to a simple single document question answering. There is a lot to RAG and various kind of architecture and different approaches are possible and different models can be integrated with it. But for now, we'll keep it limited to the simplest form of RAG, direct question answering. And we'll be using this particular PDF, World Health Statistics provided by World Health Organization for 2024. This is the open source PDF available over the internet. And before we go into the details, let's ask some questions that are relevant to it and how to approach the problem, what are the right questions to ask, how to create the model, what approach to take and what are the tech stack that are required to build such a system. So before we start building any RAG system, let's discuss the principal component of a RAG. So RAG is Retrieval Augmented Generation. So there are three tasks: retrieve, augment, and generate. So retrieve, that means there has to be a knowledge base from where you retrieve something, and then augment, that means something is getting augmented with something, and finally the generation part, that is the final response that you get. So let's discuss the architecture in details. Before we start building the RAG, we have to understand there are three basic components that are required for every RAG system. The first is a context, that is the knowledge base or indexed data. That is, this is a source of ground truth or reference from where the relevant or the required chunks of data or information has to be retrieved based upon the user query, or which is most relevant to the user query that is required to formulate or craft an answer. Next, after the index data, the next in the pipeline is the retriever. Retriever is a component that is responsible for retrieving the right chunks or the required or the most relevant information from the knowledge base. And the third component is the agent. The agent is the intelligent system that ultimately formulate and the response and generate a well-defined response which is grounded with respect to the context provided. So let's understand our use case, document question answering. So coming to this World Health Statistics document, you can see that this document is not just plain text. We have graph, charts, and we may have images. So the first question we ask is that before we create the index data that we have here on with blue color, how do I extract the information from this particular PDF? So there are different approaches for that. The open source libraries for Python, there are PyPDF and OCR versions are PyTeaser. There are open source libraries such as Markdown from Microsoft, Docklink from IBM. We can use those as well. And there are paid services from different service provider. For example, Tesseract Textract from AWS, and Azure OCR, Microsoft Azure OCR, and there is LlamaIndex. In this case, we'll be using LlamaIndex. Now, which service to choose, that depends upon the level of accuracy, the use case, the format and type of PDF documents we are using, and finally the budget and the latency of the system. So in this case, we'll be going with LlamaIndex. So let me show you how Llama, actually this is the Llama Pass from Llama, available on Llama Cloud. So Llama Pass provides some free credit which you can use for trial purpose. So if you go to their site, you can generate an API key to use their SDK. And apart from that, they give you code snippet. This code snippet will vary depending upon the configuration and use case. You can try out different configuration. You can see there are at least three different configuration possible: cost effective, agentic plus. So please feel free to try it out. and I have also tried it out on this particular PDF, and I have seen that this works pretty good. Now, the question is, before we go into indexion, how is this data available to us? You can see that according to their documentation and this playground that they provide, this data is actual. They can provide you in normal text file or and markdown format, and the tables can be converted back to markdown. And once I have tried it out, I found that actually the tables are also available as rows. That means I can convert it back to a pandas format. So now why I'm talking about pandas format? The question is, if the content of each page is directly available as markdown, then why to go into that complications? We can directly do extract information and read it in the markdown format. Well, before you start building any system, always verify what is actually happening, what is the ground truth, what is the format. Just try to visualize and verify everything. So if you see their markdown, when you try it out, the markdown they provide is actually available in the HTML format. So yeah, that is a problem because LLM are like the accuracy of a LLM system is more in a markdown format than with respect to table being provided in HTML format. So it would be better if you can get some of the markdown format. Now, how do we do it? Well, the approach is that you take this parsed output, and you can see for every page you get, for example, page 15, you get the full text and markdown. Apart from that, you get items. For each items you have type, for example, text, heading, or table. Whenever it is anything else, you directly take the markdown. Whenever it is table, we can convert these rows to a pandas data frame, and from that data frame we can convert it back to markdown. That will the formatting will be much more superior than the HTML format, and the accuracy of the output, the response generated by the agent will be much higher. So coming down to the next component, if we see here the retriever. Next is how do we build the index data, how do we build the retriever, and then how do we build the agent. Now let's focus on the coding part. How do we do it? So let's come down to this notebook. You'll find all the codes here. This will be uploaded on the GitHub. You can refer from there. Now, how do we parse it? So, for parsing the PDF, we have a simple module which will take the PDF as byte, and using the LlamaIndex, actually the Llama parse SDK, and using your own API key, it will parse you and give you back the response. Now the PDF parsing is done. Now, how do I create the index? Now, before we create the index, there are few questions that needs to be answered. So, like if the user asks a question, for example, this is the query. Now, based on this query, the relevant information, chunks of information, or the required information has to be retrieved from the PDF, and that has to be augmented with the query. And that means you are augmenting the context with the user query and providing it to the agent. So how do we retrieve the relevant information? Now let's think about different ideas how we can approach that. One approach could be that if we can create chunks of paragraph or few lines, and if we can embed them, and based on the user query we can retrieve the topmost similar information and just augment it and pass it to the agent. That will do the job, right? Yeah, but before we go there, we have to answer two questions. Now we have tables here. Now, how do you create embedding on a tabular data? We can always say that, yeah, we can convert the embedding can be created on the markdown or the text of this table, the way it is available. But will that create any meaning? Can we extract the semantic meaning from there? So, from my experience, I could say that directly creating embedding on raw table doesn't make much sense. and the retrieval pipeline, the accuracy or the retrieving accuracy will not be that high. So, and apart from that, you have to understand these are pure numbers. The context actually increases from the number of tokens generated from a plain English text and versus the number of tokens you generate on a numerical data set is much higher for the numerical data set. So that has to be taken into account. Now, for creating the embedding, how do we create the embedding? What model do I use? Do I use paid services such as OpenAI embedding, Gemini embedding, or what else options do we have? What is their accuracy? And how much can I embed? Those questions need to be answered before we can decide on the next tech stack that we are going to use for creating the indexing and the retrieval. Now let's decide on the model to embed. So we will be using Nomic embedding. This is available for free. This is an open source model on Hugging Face. At least the version 1 is open source. We can use it directly from here. Now let's focus on the embedding model itself. You can see you'll get all the scores here. And if you see the sequence length is mentioned as 8192. That means it supports maximum of 8192 tokens as the input context to create the embedding. Anything beyond that, the model will simply truncate it and create embedding based on the first 8192 tokens. So it will not generate any kind of error, it will not throw any warning, it will simply truncate it. So that information is lost during embedding and the retriever will not work function properly. So how do we solve it? How do we address this problem? And there are two problems. First, the context length is 8192, and directly creating embedding on table may reduce our accuracy since tables are more of what to say, a numerical information than of semantic information. So how do we solve this problem? Well, the approach we'll be taking here is that we'll be creating embedding based for each page. We'll be creating embedding based only upon the text provided. We will not be considering this tabular output which is available in Markdown for any kind of embedding. And once the user query is available, the retriever will retrieve the most relevant chunks based on these textual embeddings. And with each, when you create the vector index, we'll be storing the page number as the metadata, and when we retrieve the relevant chunks, we have the page numbers, and based on unique page number or the set of page number available, we will be retrieving the entire page content from there, and we'll be passing that context as the augmented context to the query to generate the answer. So that is the way how we can bypass the problem of retrieving the table, and we can also keep the context limited to less than 8000 tokens. So the technique we'll be using here is that the algorithm works. Algorithm that has been implemented is like this. For each page, will be creating chunks of 1000 words, not token, 1000 words, only on the text part, not on the table part, and the overlap will be 300 words. And based on that, we'll be creating embedding of those chunks and we'll be storing it in the vector database along with the page number of that chunk as the metadata. So that piece of code is also available. So you can see generate vector index that is available in indexing.py. First, it extract the PDF content, and once the PDF, you can see we'll be taking only the text for the embedding, but we'll be storing both text and full page markdown. If you see here that embedding will be created based on the text and based on the relevant chunk retrieved, will be using the full markdown of that page as the relevant context. So from the indexing, we have three parts. First, create the PDF, extract the PDF content uh, from the using the parser, and once that is done, we'll convert it back to the required formatting, that is creating markdown from the table. then we create nodes. This is how LlamaIndex works. Before you can create any index, you need to create nodes, and from that nodes will be creating the create nodes code is also there, as I have told you. We'll be converting into chunks of 1,000 words with a value of 300, and we'll providing page number as the metadata. And once that is done, we'll be creating vector index, and this vector index will be using ChromaDB as the vector database. This is our choice. This is available for local hosting, and we'll be using that local hosting as our required database, and will be stored in as the vector database name ChromaDB. And yeah, you can provide the database name and the collection name as well. So now we have created the indexing part. We have parsed the PDF, and we have created the vector index. Now the retriever, how do we retrieve it? To build the retriever, this is once the index is ready, the retriever works in the same algorithm that I have just said. That first retrieve the relevant chunks of information, that is the text part, based on the embedding similarity, and after that get the page number from the metadata. Based on unique page number, retrieve the entire content of that page, and that is the exact algorithm that is working in the retriever. Now let's test the retriever. So if we get here, sorry, this is the base retriever, this is get retriever. Yeah, get retriever. So here you can see, first we get the index, that is the we load the vector database into the memory, and we that index is used as a retriever. We are retrieving the top three similarity, and you see we are providing that include text equals to false, because we don't need the actual text of that particular chunk. What we will be using, that we'll be using the metadata of that chunk to get the actual content, which is the whole page markdown. And yeah, once this is done, we'll be feeding that to the entire agent, to the entire content to the agent, and that will be used as a context to generate it. So yeah, get retriever. Let's see it. Get index, retriever, index as retriever, and yeah, finally it is sending back the retriever. Now testing the agent. Process query. How do we build the agent? Well, we have a query processor where we defined an agent. We'll be using Gemini as an agent. This is will be direct question answering agent. There is no feedback loop. There is no memory. There is no tool calling, and and there are no routing. These are advanced concept of RAGs. We'll not be focusing on those as of right now. The agent is as simple as it could be. So the it works like this. You have the content and you have the query, the context, the user query. You make an API call, you get the response from Gemini, and that is the output. So how does it work? So to process the query, first we get the content. To get the content, will be first we'll get the results from the retriever. Based on the results, we'll be converting to unique page numbers using set from Python, and based on that page number we'll be retrieving the entire full page markdown, and we'll be sorting those according to the page number. And once that is ready, the sorted content is ready. Now we'll be creating Gemini content. Gemini has a particular way in which you can pass the content. You have to pass the system prompt and the user prompt separately. Here we'll be providing it in a very nice well designed format. First we'll provide the user question, then for each unique page number we'll provide the entire content of the page number, and we'll append it to the content to pass it to the Gemini. Now how do we get the Gemini response? Now remember, this code is developed with respect to our, like, keeping in mind a production grade system that you can actually deploy and run properly, like a ready system for deployment. Now, and that's why I'm coming to that. You can see we are providing await here. We are using async approach for this. so that multiple calls can be made to the system at the same time, because we will be using fast API to build this system. So the Gemini response, you see, first we get the client. This is the approach in which client is defined. You have to provide the Gemini key. We'll be using AI Studio to get the client. You can also use Vertex AI if you have the account. We are using Gemini 2.5 class, and again we are using async mode to get the response. You can see we have provided the retry mechanism with the exponential delay, and yeah, there are three retries with exponential delay in case of any error, and the configuration for generating the response is temperature we have provided is 0 and thinking budget of -1. Thinking budget -1 refers to dynamic thinking. That means the model can do internal thinking of as much as required according to the usage. Temperature 0 means we don't try to deviate too much. The creativity is reduced or the randomness is reduced for the model. This is the agent, and once this is ready, we define a FastAPI endpoint. We have main.py where we can start a FastAPI server using Uvicorn on port 8000. We are mentioning worker as 1, and we have created an endpoint of process query where query is available as a string and the response will also be available as the string. So here we are creating an object of the query class. Now why we are creating object of the query class? Because there are few things that are to be initialized at the start. This get retriever. This retriever means you are loading the entire retriever into your memory. If you do it every time there is an API call, that will create a lag in the system, that will increase the latency of the system, and it will not be feasible. You will run out of memory in no time. So once you create the object at the start, so yeah, you load the content once into the memory, and the entire PDF content is also loaded once into the memory, and you just uh, run it and retrieve it every time there is a API call. So yeah, on the initialization of this class object, we do that, and apart from that we call the class functions, and yeah, that is how it works. Every time there is a on the initialization we create the processor, and every time there is an API call hit, we just hit it and get the response. Now let's run and see it. We can simply run it by doing python space main.py, and it will start the server. Initially, it will take some time because it is loading the index into the memory, so that takes time. And one thing is that when you create the indexing, you are creating embedding using this nomic embedding. So this is a heavy processing. So initially, during creating those index, it will also take some time to do that. So, and we need at least 16 GB of RAM to support this. Uh, so yeah, now you can see the server is started. So for the test purpose, I have created a file concurrent curl.sh. So we can run this script and it will just hit the fast API server parallelly with 5 different questions. And yeah, so let's run this. Actually, this will execute 5 different call commands with different. I have already tested it out. Let's test it once more. Yeah, you can see it is hitting the local host, and yeah, it is doing parallel calls 1432. This is the sequence of the questions and how much time it is taking for each response. So you can see the total time taken is 13 seconds and all the answers are ready. So yeah, so that means the first API server is working. You are getting all the response. It can handle parallel request at the same time. Yeah, and you are getting all the response back in short time. So this is how you build a production grade system on a RAG system. Now this is the simplest version of the RAG possible. There is a lot to RAG system than just doing simple question answering on a PDF. For example, let's extend it to what if there are multiple PDF, and There are actually so many. There are routing strategies. There are different retrieval strategies. There are agents with loop. For example, there can be self-reflection loop. There can be feedback loop, like human in loop, and yeah, there has to be memory. For example, this has no context of past question asked. So if you ask, and there has to be sub-query decomposition. For example, there are multiple PDFs and you want to ask, well, compare this from this PDF with this. Those things are not there. There are no tool calling. So there is a lot of things that goes into the RAG. But if we understand the basic, we can slowly build the most complex RAG system that is possible. And yeah, so from this material, we want to focus on three key components of the RAG. First, we need to have a knowledge base, some kind of indexing on the data such that we can retrieve the relevant chunks as a point required. And there has to be a retriever. A retriever is a component that, given a query or situation, that can retrieve the relevant chunks of information from the knowledge base, and there has to be an agent. The agent is the intelligent system that will formulate the answer for you and give you a well-defined, grounded response with respect to your context. So these are the three primary components. If these three primary components are well designed and well integrated, then the RAG system will work smoothly. So that is all. Uh, Feel free to try it out, try different approaches, try different models, different combinations. How do you create the context? This is one of the contexts that I have defined. Is there any better approach to create the context? Of course, there are better approach. You can try it out on this one from the Llama Parse side. Try out their different configuration, which gives you the best a response with respect to the PDF. Now for the agent, we have used Gemini model, and of course you can use different other versions of Gemini models, as well as source model, for example Llama models, or you can also use OpenAI models, GPT models. And apart from that, for this agent, we are passing a context of three pages, because the Gemini 2.5 models support a input context size of 1 million tokens, and 3 pages will always be less than that. And these 3 pages are at max because we are passing the content of unique pages. So it will be always less than equals to 2 pages. And we have provided a basic system prompt. You can always upgrade it, improve it according to your use case and requirement, as well as the context template, like the format or the template pattern in which we are passing the input, that can also be upgraded and tuned according to the particular use case.